Hello everyone, this is Anna Bartkiewicz at Nicolaus Copernicus University in Torun, Poland. I'm very happy to welcome you on behalf of the organizing committee to this second series of seminar sponsored by the European VLBI network focusing on high-resolution radio astronomy. Let me mention a few logistics. You will be muted throughout the presentation, but you are invited to type in any questions you may have for our speaker through the Q&A Zoom facility or in the chat at the YouTube channel. Questions will be answered only after the presentation. Please try to write your questions clearly and keep them short. We will aim to get to as many of your questions as we can, and we apologize in advance if your question is not among those we have time to answer. Before we start, please remember to register for the 15th EVN Symposium and Users Meeting in Cork that will take place on July 11, 15, 22. Now, Miguel Perez Torres from the Instituto de Astrofísica de Andalucía will introduce today's speaker, Juan Climent.
Hi, everyone. It's really a pleasure to introduce Juan, who recently, well, not recently, 2 years ago already, defended his PhD thesis. He actually finished his physics studies in 2014. And then he moved to the University of La Laguna in the Canary Islands, where he got his master thesis. And then he went back to Valencia, where he started his PhD thesis under the supervision of Dr. Guirado on, interferometry studies of low mass stars, also on other even cooler objects, ultracool dwarfs. Also testing models using near-infrared interferometry. So he's really an expert on reinterferometric studies. Today, well, actually, as I said, 2 years ago, he defended his PhD thesis, and now he is a postdoc at the University of Valencia, where he continues the collaboration with Dr. Guirado. He also collaborates with my group at the Institute of Astrophysics and Andalucía in Granada. But he also has collaborations ongoing with the ESO working group on near-infrared interferometry. So today, we have the pleasure to listen to his most recent results obtained using, in particular, VLBI, the VLBI technique, particularly the EVN, on a number of low-mass stars. So I think that's everything. I now give the word to Juan, and thanks a lot.
Thank you, Miguel. The pleasure is mine. Can you hear me properly?
Yes, we can hear you.
Yeah, perfect. And now let's share my screen. And hope that you can see full screen.
Yes.
Perfect. So thank you again. Yeah. So my name is Juan Climent from the University of Valencia in Spain, and I would like to, of course, thank the organizers for the invitation to spend a few minutes with you, and while sharing the interesting field, I think it's interesting, of radio emission in low mass stars, ultracool dwarfs, and also exoplanets, always at the highest angular resolution. Now, following our innate curiosity, we have observed the skies at every available frequency. Even when our atmosphere did not allow us to investigate at certain wavelengths, we launched satellites and missions to overcome this barrier. From this great endeavor, we now know that, there's a wide range of stars that emit at radio frequencies, as you can see from this HR diagram. These are detections at, megahertz, gigahertz. From big hot stars to young T-Tauri and even low mass stars or brown dwarfs. Today, we will focus briefly on low mass stars, but mostly we will go beyond them and investigate the radio emission on brown dwarfs and even exoplanets at the highest angular resolution. Now, first, despite what this HR diagram might make you believe, detecting radio emission from stars other than our sun is not guaranteed. Yes, we detect a great variety of objects at these frequencies, but not a huge number of each type of object. This is especially in some of these objects, okay, in some of these types. However, radio observations are very informative as they can reveal stellar flares, coronal structures, colliding winds in binaries, while at the same time allowing us to measure the proper motions, parallaxes, and orbital motions of different systems. Now, in all of these systems of this HR diagram, radio emission is related to high energy electrons and magnetic fields. So that's pretty simple origin, right? Yeah, but always, yes, but there are many mechanisms. Here you have a list of most of them. And the majority of the time, it's quite difficult to discriminate between them, which ones are operating, basically, your object. Some useful pieces of information that can help you dismiss at least a few mechanisms are the brightness temperature. As you can see from this list, the different brightness temperature can help you. So it can help you say, at least, for example, it's not free emission, it's not incoherent epsilon, because my brightness temperature is 10 to the 7 Kelvin, for example. But there's another useful piece of information, and that is the degree of polarization. Of course, one of the biggest and perhaps most useful pieces of information is the spectrum of the emission that you are detecting, as you can see from this plot. Throughout this presentation, you will see real examples of the complexity of distinguishing mechanisms, but I'll try to make it as clear as possible. But first, we're about to explore the skies at the highest angular resolution. So a brief reminder of how we are able to achieve such great resolutions at radio frequencies. The very long baseline interferometry, or VLBI technique, is what we use to obtain the first image of a black hole, for example. I'm sure you all here will remember just a few years ago. The basic idea is to have all the antennas of an array like this pointed at the same source, and as the light emitted from the object arrives at different times on the antenna, on different antennas, one can use this delay, this time delay, to obtain an angular resolution as if you were observing with the telescope the size of the largest separation between antennas. In this particular animation, it will be the size of an Earth-sized telescope, basically. Now, one of the first VLBI contributions to the radio star field was the discovery of a compact core plus extended halo radio structure. This was seen in error CDNs and algo-like binaries, but a few years later, Benz and collaborators discovered that the flaring M-dwarfs UCD is actually surrounded by a pair of giant synchrotron lobes. Although the location of the star here represented with a white circle, was just a hypothesis back then. All of these results clearly prove the existence of a very extended magnetic structures in these objects. Now, following this work, we study the evidral system. Stars with masses lower than our sun are quite common in our galaxy, and so are binary systems. As such, I find it suitable to present to you this binary low mass system that is quite close and quite young. Look, it's just 15 parsecs away and between 30 and 150 megayears. Evidral A, the main star of this system, is a K0 star that is rotating considerably fast and has a much lower mass companion with a spectral type M8, and that will give us something to talk about in a few minutes. Now, it's very important to know that the orbit of the system, the orbit of evidral C around evidral A, and even the reflex motion of evidral A is quite well determined. It's well known from astrometry campaigns at radio frequencies, also some HIPAC satellite data. And here you have the in this table some of these values to consider that describe this orbital motion. Now, with a campaign of VLBI observations, using in this case the long baseline array, because the object is minus 62 degrees declination. We observed for more than 10 years, covering frequencies from 1 to 22 gigahertz. And we found that the main star of the system, AB/A, is actually presents an extended structure, at least as you can appreciate from the three images at 8 gigahertz. And thanks to the great precision that the astrometrically determined orbit, we know that the star actually is here on the red crosses, where the locations of the red crosses. Okay, now this is important. But first, in 2007 and 2010, so these two images, you can see that two components are clearly detected, with the same separation and orientation. In 2013, however, the orientation is still east-west, but three components are detected at different separation. All of these components at 8 gigahertz are consistent with synchrotron or geosynchrotron emission. Now, to explain the origin of this structure, this extended structure, we consider different scenarios: emission originating at the poles, like what has been proposed for UCD, and I already showed you; emission coming from equatorial loops, as was simulated by Cohen; emission similar to a helmet streamer, as was proposed for B773WA, or even a close companion hypothesis that we could actually dismiss in our work due to the temporal analysis of these very images. In any case, for more details, I'll have to direct you to the publication, because now I'd like to go to objects with even lower masses. Now, you may have noticed that I did not mention AB/C, this M8 companion, right? This is because we did not detect any radio emission coming from this object, suggesting that when one goes to lower masses, radio emission may not be so easy to detect. However, detections of these lower mass objects are crucial for various reasons. First, evolutionary models desperately need more dynamically determined masses at this very low mass regime in order to benchmark these models. And here, VLBI observations are extremely valuable. Additionally, and as we will see in a few minutes, radio observations may allow us to discover and even characterize exoplanets around M-dwarfs. And finally, the Tacoc line, that is the layer between the radiative and convective zones of an object, disappears at a certain mass. As you can see from these simulations of a sun-like star and a fully convective object. And with the Tacoc line, one would expect to lose also part of the magnetic field strength and the associated radio emission. But that's not what happens. The first discovery of radio emission from a fully convective object, from an ultracool dwarf, actually, in 2001, proved the existence of powerful magnetic fields and radioluminosities, orders of magnitude higher than expected. Indeed, if you take a look at this graph, this plot, the expected radio emission is shown here with a red line, and it is known as the Benz-Gödel relation between radio and X-rays. And here are some objects that clearly challenge this prediction. Now, during what remains of the talk, and I already introduced it actually, you will hear the term ultracool dwarf a lot. So let me define it here. Ultracool dwarfs are objects with a spectral type later than or equal to M7. And some ultracool dwarfs show, let's start firstly because these objects are fully convective, as you already know, and have masses that can be as low as 15 to 20 Jupiter masses. Like Proxima Centauri or Theta 1 that just passed by in this animation, the sizes of these objects can be comparable to that of Jupiter. Perhaps if it starts again, you can see this is the Sun, and as a comparison, here you have the size of Proxima Centauri. That would be Theta 1, the first ultracool dwarf discovered, and then Jupiter. Now, I was saying a lot of radio observations of ultracool dwarfs have been made during the past, and here you can see that most of them resulted in no detections, represented here by the blue triangles. Some ultracool dwarfs show a quiescent or a stable emission exclusively, while others also reveal the presence of flaring emission. Let me give you a brief summary of what we have discovered so far in regards to ultracool dwarf radio emission. Now, from this image, you can imagine that, well, some ultracool dwarfs produce radio emission at gigahertz, but some don't. If we take some numbers, actually, it's estimated, it's an estimation, that around 10% exhibit radio emission at 1 to 10 gigahertz, although this value seems to increase to nearly 50% for fast rotators. Ultracool dwarfs can also possess strong magnetic fields of up to a few kilogauss, quite strong, and we have direct confirmation from this based on spectropolarimetric measurements, but they can also be inferred from radio detections if you correctly identify the mechanism underlying the radio detection, of course. Now, the most important thing is that the radio emission can be in an ultracool dwarf can be separated into two components: a quiescent or stable part, which is almost always present and with a low to moderate degree of circular polarization, plus a rotationally modulated burst emission here, these auroras, that is present only in some of them, and which is typically highly circularly polarized. Now, we usually explain the radio emission in these objects by the geosynchrotron mechanism for the quiescent component and a coherent mechanism, such as electron synchrotron mass instability or plasma radiation for the burst emission. Although this picture is far from complete. For example, Hallinan and collaborators showed that the quiescent component of one particular ultracool dwarf couldn't be explained with the geosynchrotron mechanisms, but it was well explained with electron synchrotron mass instability that becomes depolarized as it propagates through the ultracool dwarf magnetosphere. But beyond the interesting science of ultracool dwarfs themselves, that we will go into in detail in a few minutes, it is important to notice that the knowledge gathered from these studies will be crucial for detecting could be crucial for detecting direct exoplanetary radio emission. Additionally, we expect some signatures of star-planet interaction. For example, burst in emission on the dwarf, on the ultracool dwarf, but that is modulated by the presence and the orbital period of the exoplanet, similar to what happens with the Jupiter Io system. In this sense, here you have a theoretical model of such interaction, here on the left bottom, for Proxima, actually. This is some numerical work for Proxima Centauri, with predicted fluxes for the burst in emission that is represented in dashed lines, clearly detectable with current instruments. And here on the top right, on the bottom right, you have some work done by Miguel Pérez Torres, actually, and some observations that show a tentative detection of this type of star-planet interaction signature, also in Proxima. Now, dozens of ultracool dwarfs have been detected at gigahertz using single dish or small arrays, small like ATCA or the VLA. But what about VLBI observations? Well, TVLM 513, let me call it like that, was the first confirmed detection of an ultracool dwarf with VLBI arrays. The object, actually, if you take a look at this image, may have been resolved, but the noise was too high in these observations to conclude anything. Actually, follow-up observations did not report any extended structure, but still, nevertheless, this is an important result because it opened the possibility of looking for companions by measuring the reflex motion with an astrometric campaign. This is actually what Salvador Curiel in 2020 presented with observation in the same object, TVLM. But last thing you can see here, all the dates, almost 10 years, and the residuals of the astrometric analysis that they did indicate the possible presence of a companion with these characteristics. But counting TVLM, there are only 3 published detections of ultracool dwarfs with VLBI arrays. So the other 2 that we know so far is this one, this binary L0 plus L1.5, where both components show radio emission. And this is the other binary where only one component was responsible for the detected radio emission. Despite these few detections, they are extremely useful as they can determine dynamical masses, resolve whether the emission originates in one or both of the components, provide precise parallax and proper motion, and even investigate the presence of exoplanets around them by astrometric campaigns. All of these points that I just rapidly said, they take some time, but they can be right now investigated. In our team, we just published an interesting study of an ultracool dwarf system. Actually, it's a triple system, VHS 1256, 1257. It is one of the few systems where all of the components are substellar, and it is relatively young and nearby. From our previous work in 2018, we knew that the central binary emits at gigahertz frequencies. And so we proposed a multi-frequency, multi-epoch campaign to better understand the radio emission. Now, the L7 companion, the lower mass companion, was not detected previously and is still not detected with the new campaign. We used Merlin, EVN, VLA, NOEMA, and ALMA data, and only detected the binary with the VLA as an unresolved source, as you can see in this image. So, a useless non-detection with VLBI arrays? Not really. Thanks to the EVN data, even with no detection, we could place strong upper limits on the physical size of the emitting region. Actually, we use this piece of information in our work to discover that both components of this binary system must have a very similar flux ratio lower than 2.7, basically. And additionally, after considering a lot of possible scenarios to explain all the detections, non-detections, polarizations, etc., our data seems to indicate that the emission of this binary is due to geosynchrotron emission originating possibly at radiation belts around both components, similar to those of Jupiter. But besides the no components that did no detection, that are still useful, I am very happy to say that the number of ultracool dwarfs detected with VLBI arrays is increasing rapidly. In this sense, our team has started a campaign to study the compact emission of 4 new ultracool dwarfs with the EVN at 5 GHz. And we found clear detections in all of them. We based our criteria on the fact that there is a much greater possibility of detecting radio emission if the object has a rotation period lower than 4 hours, which would be this line in this plot. As you can see, the majority of green triangles, which are the detections, are below this line. Now, let me show you some results of these campaigns, the ones that we have so far. This is the coolest ultracool dwarf ever detected with a VLBI array, with a spectral type of T6 and only around 30 Jupiter masses. Of the 2 epochs radio, we have 2 epochs, 2019 and 2021. And radio observation is detected only in one of them, in 2019, indicating a clear variability. This might be because we detected a burst during the first epoch. However, we covered more than 3 full rotation periods during the second observation and found no detection, which is intriguing, as the pulses, these peaks, are expected to have the periodicity of the rotation period. I should mention that the detected emission in 2019 presents a high degree of circular polarization and is only detected during the first half, the first hour of observation. But no single rapid pulse is detected. Now, this seems to agree with the VLA light curve of these objects reported by Williams and collaborators in 2017. And in this case, no single pulse is detected, as you can see, but it's rather complicated. It's a rather complicated light curve with multiple features in it. To explain this light curve, the author suggested that the magnetic axis and the rotation axis of this object would be misaligned. Here you have the rotation axis in black, and the magnetic poles, let's call it like that, would be this, for example, this bluish circle on the surface of the ultracool dwarf. And so if this rotation axis and magnetic axis are misaligned, the magnetic poles rotate in and out of the line of sight, producing this light curve. But this is okay, understandable, but what are the possible explanations for the non-detection in 2021? Well, as proposed by Root in 2016, even ultracool dwarfs may present magnetic cycles similar to the solar ones, where the polarity reverses, going, of course, under a period of no expected pulsing radio emission. But also, another possible scenario is not that the intrinsic magnetic field changes, but rather that it is modulated by the presence of a companion. It has been proposed for the pulsing emission and also for the coronal emission. And in this case, the companion would need to orbit this ultracool dwarf with a period greater than the observing time of 2021, that is 9 hours. In this sense, a VLBI astrometry campaign will follow this intriguing object, from where we will be able to detect or dismiss the presence of a companion like more massive than Saturn, with a period of greater than 150 days, or a Jupiter-like companion exoplanet at periods greater than a month. Another new detection that we made in this campaign is on a binary system, LP34925. And in this case, we detected a radio emission from both components at 2 different epochs, but only one of the components at another epoch. The reason for this variability is actually right now under examination. With this, it is clear, however, that with these detections, these valuable detections, a full astrometric analysis will provide extremely precise dynamical masses to test evolutionary models. Now, this is another detection, and it's actually a confirmation of the compact nature of the pulses that we were seeing in ultracool dwarfs. In this case, an L3.5 object was detected with the EVN at 2 different epochs, again, 2019, 2021, and they have similar intensities showing in the light curves, showing clear signs of highly polarized burst emission. As expected, these pulses are related to the rotation period of the dwarf. And take a look that they don't show any clear signs of additional modulation. It's just the modulation of the rotation of the dwarf. And perhaps saving the best for last, these are EVN detections of an MA.5 object that shows as well rotationally modulated pulses. And here actually you have the light curve in 2019, here in 2021. And when in 2019, almost an entire rotation was covered. In 2021, you have 2 full rotations. In 2019, and the first 2021 pulses show a 70% left circular polarization, which is compatible with the auroral activity that is proposed for this object. The detected large left circularly polarized peaks seem to be preceded by a smaller right circular polarizations peaks marked with red arrows in this figure. This fast change in the pulse polarization can be geometrically justified with the presence of a dipolar magnetic field whose axis is tilted with respect to the rotation axis, as sketched here. Now, the second peak in 2021 is different in intensity and degree of polarization to the other ones. indicating a possible modulation or a geometrical effect. If we image the quiescent component, that is, if we remove the pulses from the data and now image the remaining data, we get this image for 2019, and this image for the first full rotation of 2021 and the second rotation of 2021. The low degree of circular polarization and the persistence of the quiescent emission points towards a geosynchrotron mechanism. Now, remarkably, as you can see clearly, during 2021, a complex structure is resolved in the quiescent component. Now, if on the contrary, now we use exclusively the data from the bursting periods, here shadowed in the light curves with a gray shadowed rectangles, the maps show basically unresolved sources that are represented in the images below with black circles. Now, the sizes of these circles are those expected for the photosphere of this object. And they allow us to pinpoint where the auroral phenomena is originating within the extended quiescent emission. Now, this is not all. The circular polarization images are puzzling, even more puzzling, at least to me. During the first rotation of 2021, here in these images, the quiescent extended structure can be interpreted, let's say that there are two components, right? Component A and component B. The A component has a great degree of left circular polarization, as you can see here, whereas the B component has a great degree of right circular polarization. So both components have opposite polarization. That's great. But what's even more intriguing is that the location of the pulsing emission, that remember is clearly left circularly polarized, is closer to the B component. During the second rotation of 2021, the peak in the light curves was not so clear. And so the black circle here in these images below still represents the pulse during the first rotation, okay? That is the expected position, more or less, of the photosphere. Now, in this rotation, the opposite polarization in the quiescent components does not seem so extreme, although we are right now under an exhaustive analysis and trying to, well, because the data quality is actually not as good as during the first rotation. Now, in any case, how do we explain these beautiful images? Well, I still cannot present you a definitive answer because I don't know, basically, but I would like to share with you some hypotheses that we've been working on lately so that you can criticize them or share some thoughts during the Q&A. Let's focus firstly on the quiescent emission, okay? The great question here is whether the emission that extends 25 stellar radii, approximately, is tracing the polar regions like the model proposed for UCD or Argon right here or not. So in this scenario, components A and B of this quiescent emission will be, of course, readily associated with emission coming from different poles. So this would generate component A, and this pole would generate component B. Alternatively, it could be tracing, actually, we could be tracing equatorial belts, similar to those of Jupiter's synchrotron, here shown in this animation, and that are morphologically similar to what LOFA has been able to image on Jupiter, right here in these images below. Now, which one of these is correct? Well, I already told you, I don't know. Perhaps you can help me with this. But, well, there's no direct measurement of the rotation axis inclination of this object. But if we take the known rotation period, the known rotation velocity of 50 kilometers per second, the rotation period of 2.84 hours, and the predicted radius, we get an inclination of 33 to 100 or 147 degrees. These values are important, as they imply that we are seeing only one pole of the object. Now, let's see if you can follow me. If the pulse is originating close to the photosphere, as expected, then we can associate the black circle with the photosphere, okay? Yeah. Now, one more assumption. If the polarity of the pulse is associated with the polarity of the large-scale dipolar magnetic field in that hemisphere, as occurs in sunspots, you would expect a left circularly polarized pulse in a left circularly polarized hemisphere. This means that we are not seeing the polar emission in the quiescent part. Otherwise, we cannot explain this image. Therefore, if these assumptions hold, which is a big if, we are looking at the first ever resolved radiation belts in an ultracool dwarf. Of course, all of this is right now highly speculative and could be thrown away after the Q&A. But it is now time to explain the pulsing emission. This was all about the quiescent emission. Now let's explain the pulses. Well, the usual mechanism invoked here is the electron cyclotron mass instability. But what is the trigger? What is triggering this mechanism? Well, this is currently under discussion in the literature. Saul and collaborators propose that these pulses are driven by internal processes, where the strong magnetic fields and high rotation results in magnetic loops where this emission would occur. Hallinan raised the possibility of an external origin, where the pulses will be generated after the interaction between the dwarf magnetosphere and an exoplanet. These authors actually suggested that an Earth-sized planet, at least, located at 0.01 astronomical units, could generate the observed auroras. Interestingly, the proposed separation corresponds to 1.8 milliseconds, meaning that the possible exoplanet generating the auroras would be located within the extended structure seen in our VLBI maps, somewhere around here, for example. However, as happens in Jupiter, and that's why I said I plotted this beautiful illustration, these induced auroras would be modulated by the orbital period of the companion and also the rotation period of the ultracool dwarf, of course. Now, right now, the only evidence of a possible modulation in the pulses could be a light curve in 2021, so this here. But even if the pulses are not induced directly by an exoplanet, the presence of such companion could be necessary to explain the constant supply of plasma necessary to generate the auroras. Again, as illustrated in this picture of Jupiter and Io, where you can, here we go, Jupiter and Io, where you can distinguish actually the aurora directly induced by Io here, and the fact that this volcanic moon creates a lot of plasma that then produces the current that results in the main oval. Therefore, this possible exoplanet in this ultracool dwarf would be a prime candidate to act as the source of plasma that can eventually produce both the geosynchrotron quiescent emission and the pulsed emission as seen in this case. Now, before leaving some time for the Q&A, I would like to know that the work presented here has not been done only by me, of course, but by a team of researchers. So thank you, Jose Carlos, Miguel Ángel, Marcaide, Luis Peña, etc. But summing up all that we have learned here, I hope it is clear that the field of radio emission from low mass objects with VLBI has a huge potential. Thanks to the capabilities of the EVN, we can now measure the dynamical masses needed to benchmark evolutionary models. We can provide accurate parallax and proper motions with astrometric campaigns. We can apparently resolve the magnetosphere of these intriguing objects and even investigate the presence of exoplanets by proper motions or by star-planet interactions. Now, first of all, thank you for your attention. And second, if you have any questions or anything that is not clear, I'm here to help you. Thanks.
Thank you, Juan, very, very much. It is nice to see so great results from this very sensitive and very good EVN array. Yeah. So first we start from the questions in chat. Can you come back to the slide 10? It was a technical question about the red position. Does it comes from the Gaia DR2?
Hold on. Slide 10 is this one. Yeah. And
about this red point.
Oh yeah, the red point, yeah. And this is using, let's see, Hipparcos Hipparcos, I think it's pronounced like that, Hipparcos satellite data, so basically infrared and radio data, radio interferometric data for, I don't know, it's like a couple decades, I think. And that's why we get so much precision in the, we know the orbit so well.
Okay.
I don't know if this was, it was in the chat, right?
Yes, yes, at the very beginning. So
oh yeah. Joe, no, it was not from Gaia, sorry, yeah.
Okay, so the next question in chat, do you know what the two stellar rotation phases are for the UCD, where you see the emission disappear in 21?
In 2021, okay, so the UCD where you see the emission disappear, let me go there. Sorry for the DC slides. So I don't know which one you're talking about. It's the detected. Oh no, this one. Do you know where the two stellar rotation phases for the Tucumán where you see the emission disappears? You mean Rob? This was from Rob, right? So Rob, perhaps you mean this one, where you don't see any ultracool dwarf emission in 2021. Perhaps it's this one. In this case, yeah, we know, well, actually, we don't know the exact phase, if you mean that, because the phase rotation, because actually the rotation period is not clear. So you can see in this is the only object that has a wide range of possible rotation periods. So we don't know, but even the highest value of 1.93 means that you have, yeah, this was 9 hours of observation, so more than 4 full rotations. Well, yeah, I don't know if this helps you. Yeah, back at the okay, yeah.
So in the chat. So the next question in the chat is the detected level of circular polarization for LSR J1835 plus 3259 consistent with the radiation belt hypothesis?
Thank you for reading that, Anna. Yeah, we're still checking that, actually. At least the first, this was actually done last week. So you can imagine that we are now looking at the morphological similarities. And now it is that question that we are trying to answer. Is this first the polarity? Perhaps I can show it. Yeah, here. So this polarization, this different polarization, I still don't have a number. I know that clearly they are, the A component here is left circularly polarized, the right component, the B component is right circularly polarized, but I can give you the number of 20% polarization, 50%, I still don't know. So that's the first thing. And then we check if it makes any sense with the radiation belt hypothesis.
Okay, so and again, about this topic, how large would that imply the radiation belts would have to be from your observation of your last source, if that is the case of the emission?
Yeah, that's a very good question. Actually, in Jupiter, it's just a few stellar radii, as I understand. But here, the separation here you have is 25 stellar radii long. So it would be, if the object is right in the middle, and you would expect almost a 12 stellar radii of radiation belts, which is huge. But you have to also consider that this object is not Jupiter. It's 50-something, at least, Jupiter masses in a very, very fast rotator. So there's a huge, strong magnetic. Actually, in this object, if I remember correctly from some work, it was estimated to have a magnetic field strength of around 3 kilogauss. So yeah, it's quite different.
Do we have questions in the Q&A, so we can also maybe open, it would be easier.
Oh, yeah.
So we have appreciation of the very nice talk. Regarding the cycles in the UCDs, I suppose that if the magnetic field flip polarity, you would see a change in the direction of circular polarization. Has this ever been observed?
The magnetic field polarity. Okay, you mean Aline? Sorry, Aline. I think it was when this hypothesis made by Root. I think you mean this. if so, no. The paper, this work, shows tentative evidence for some ultracool dwarfs that have been actually, one can see the reverse in the polarity of the pulses. Actually, in this interesting object, sorry to come back again, in this LSR, this one, yeah, it was first detected as with left circularly polarized pulses. Then it was no detected. There was no pulses detected. There were no pulses detected. Then the pulses were detected with right circular polarization, and then now back in 2019, 2021, with left circularly polarized pulses. So this might be indicative of that, but it's not. It's not clear. It's not the only possible explanation.
Thank you. And the question, the Q&A again, how well do you know the position of the photosphere, the black dot in your VLBI images? Probably you know it from the infrared astrometry, which is not accurate as the VLBI.
Yeah, thanks for the question. And actually, yours from Harris, sorry, I still don't know you personally, but I read your work. It's very interesting. Yours was one of the work that I have to leave out because of time constraints. So the position we measured the peak. Actually, I still don't know. I'm not fully liking these images because the peak, this black circle represents the peak, which has a great how do you say, great precision, but basically from the VLBI images, because you can get, thanks to the quasar reference point, you can get very good precision, but I have to take into account that there's, and the peak is I mean, it's resolved, sorry, let me go back. It's resolved, it's not resolved, sorry, it's unresolved, so a point like, but it's still, I don't like the fact that we are taking just one pixel. Let's call it like that. Okay, it's not one pixel. So I still can't tell you how well we know or how bad we know this. But yeah, I'll take that into account when we perhaps we can discuss it later about yeah, finding the best how best to estimate the position of the photosphere. Sorry, which I don't think it's easy. But yeah, thanks for the question, Harris.
Okay, and there is also a comment that maybe there is no need to assume that, I don't think you need to assume that the extended emission and the pulsed emission must have the same polarity if they originate in the same magnetic hemisphere. So even if the magnetic field direction is the same, gyrosynchrotron and ECME can have opposite polarity.
Ah, I see. Okay, that's great. That's a great comment. Thanks. Yeah, that's great. So, I told you that we can dismiss the hypothesis before we finish. So thanks.
Yeah, so it's very, very nice work, and it's good that more can be done. So so see you soon, maybe on the EVN Symposium, and please thank you again, Juan, and please remember that in a month we have another EVN seminar by Mar Methua, and also, so let's see, 5th May. And also, please remember to register for the 15th EVN Symposium and the user meeting that will be held by the University College Cork in Ireland. So we invite you on behalf of the LOC and SOC and Professor Denis Gabuzda. See you. Thank you very much.
Thank you, Anna. Thank you, everyone.